So we get Rlc circuits in a few forms, and it is R and a resistor and an inductor. You can get it like that, or you can have a resistor and a capacitor. Then you can have the whole thing together. Uh, a resistor, an inductor, and a capacitor. You can have all together. Then the formula that will include and exclude whatever is not there. Okay, so in this circuit over here, we have a resistor, an inductor, and a capacitor. We have AC supply, then this is our voltage total, and we have our current, our I total. So in a series circuit, the current is constant throughout the whole circuit. Throughout the whole circuit, the current is constant. So because they are in series, each of them, they have their own resistance, right? And when a component has resistance, it must have a voltage drop. And that voltage drop is named VR for the resistor. The, the inductor has a voltage drop called VL. Capacitor has a voltage drop of VC. And the sum of these voltage drops will give us our total voltage. No, not the sum, not the sum. Not the sum, right? Because each of them have their own phase angle, as you can see over here. So for a resistor, the current is in phase with the voltage, in phase with the voltage. For a inductor, it is that simple. If you guys can remember, it is that simple. So for an inductor, voltage is leading the current, as you can see over here. Um, Voltage is leading the current, so it's going like this. See the direction of the is it going? No, yeah, it's wrong with the arrow. The arrow is the wrong way. Voltage is leading the current. So if we're going this way, that way, right? There's not the arrow. The voltage of the inductor, it's ahead of the current. For the capacitor, current is leading the voltage. So the current is ahead of the voltage. The voltage is coming afterwards. And just to add, the voltage is leading the current in the inductor by 90 degrees, and the current is leading the voltage of the capacitor also by 90 degrees. Not that this plays a difference in our calculations, but just for you to understand what is meant by leading and lagging of the voltages and currents. So, as you can see here, the voltage of the inductor, it's on the top. It's on the top, right? The voltage of the capacitor, it's going under the graph, and then the voltage of the resistor, it is going in phase with the current. And the current, it is all equal to each other. IR equals IL equals IC, because the current equals I total, because the current in a series circuit is the same throughout, is equal throughout. So here's our graph of our entire, this is our phasor diagram of our RLC circuit. Then to simplify this, we say that these vectors are going in the opposite direction. So VL can be at the bottom and VC can be on top, but it just depends on their values. So we subtract the, the, the small one from the big one, whichever. VC can be bigger, then we put VC minus VL, but in this case our VL is bigger, just for the explanation. Then just so fall away, there's nothing here at the bottom. Then we're left with something that looks like this. VL minus VC. Then to get our voltage total, we do basically we do Pythagoras. Pythagoras. We do Pythagoras to get our voltage total. Our voltage total. So let's write our let's write a couple formulas that we are definitely going to use. So the first one, let's start here. Um, Let us start. So let us start by R. R will be given in ohms, and what did I say? I said that because each of them have a resistance, they'll have a voltage drop. So we are always going to use the resistance values of each component, and we are normally going to be given the value of the component in the form like of, so inductance in the inductor is measured in Henry, so we're going to get the value of the inductor in Henry. So we must convert Henry to um, it's called inductance, inductive reactance. Inductance is in Henry and the inductive reactance is in ohms. So we'll get to that. Um, yeah, okay. But the capacitor also, the capacitor's value will maybe be given in microfarads or nanofarads. Then we must convert that, or yeah, we must convert that into capacitive reactance measured in ohms. Capacitive reactance is the resistance of the capacitor. Inductive reactance is the resistance of the inductor. The resistor has ohms already, so it's as it is, as it's supposed to be. Then we use 50 hertz because 50 hertz is what we use in South Africa, in our homes, in our buildings, everywhere. 50 hertz is our frequency. So why I'm using frequency? Because we're going to use frequency to get our inductive reactance and our capacitive reactance. So we're going to start. So we're going to start here now. We're going to go here. For inductance, our inductive reactance named XL, that's our inductive reactance, equals to 2 pi FL. So 2 times pi times the frequency of 50 hertz or whatever they give us, multiplied the with the number they give us for Henry, the amount. Number 2, for capacitive reactance, it's XC equals to 1 over 2 pi FC. 1 over 2 times pi times the frequency of the circuit times C, the capacitance. Then for the voltage of this one here, we're gonna have V for the V total, right? For the V total, V total equals. Again, we're gonna use Pythagoras. voltage drop of VR squared plus the voltage drop of VL squared. Pythagoras is right. For number 4, our V total is going to be VR squared plus VC squared. For a big one, for the big one, you must pay a bit more close attention. Alright? We are gonna use this here. Remember I said over here, whichever one is bigger, we're gonna subtract first. It can vary from circuit to circuit, but we subtract. And how we gonna do this with oh, it's here already. Yeah, it's here already. It's gonna be like this. Vt equals VR squared plus VL VC squared. Now I put this sign like this. This sign tells me that depending on which circuit I have, if VC is bigger than VL, VC must come in front here and VL here. So I must subtract VL from VC if VC was bigger. And in this case, we say VL is bigger than VC. So we say VC is subtracted from VL. It's just a subtraction there from whichever one is bigger. So we have our voltages now. We have our reactances. Now we need for reactances I should have put under there, but we put it here. We need our total resistance of the circuit. And to get that, we have something called impedance. And it's written with a Z. Impedance equals. For the impedance of this one over here, we're gonna say R squared plus XL squared. So the resistance of the resistor squared plus the resistance of the inductor, which is inductive reactance over there. Number 7 for this one over here, very same thing. The resistance of the resistor squared plus the the capacitive reactance of the capacitor squared. Give us that formula over there. For the big one, it's very similar to the voltage again. Equals to R squared plus XL XC squared. Right? Very, very similar. It's basically the same thing. So now we have our voltage, we have our resistance, we have our voltage, our total voltage. We have, okay, let me use a red pen, yeah. We have our impedance. This is circuit total resistance. Okay. So we have our resistances, we have our voltage. Only thing we need now is our current. And we're gonna do Ohm's law. So I total equals to V total over Z. Total voltage of a total resistance. So we can't just get, okay, we have to calculate, we have to calculate our voltage drops, right? Our voltage drop VR, voltage drop VL, voltage drop VC. So we get that very, very easily. So we now know that the current through the circuit is it's the same, right? It's the same here because all the components are in series. So for the voltage drop of the resistor, VR equals I total multiplied by R, the component resistance. For the voltage drop of VL, I total multiplied with the resistance of that component. And this component's resistance is called XL, inductive reactance. Number 12, with the voltage drop of the capacitor, you say the current going through it, which is called I total, multiplied by this component, by the capacitor's resistance, called XC, capacitive reactance. Then we have, I want to put maybe all of them in here. I can't really, but number 13. Number 13 is if they ask for the, what's the name of that? Yeah, it's called the phase angle. The phase angle, which is this angle over here, all right? So that's gonna be, we're gonna get that by saying theta equals to second function cos R over Z. For number 14, for our resonant frequency, or you can say FR equals to 1 over 2 pi square root LC. So L and C and L times C. So L is our inductance and C is our capacitance. So L is our value of our inductor. C is the value of our capacitor. These formulas we will definitely be using to solve our RLC circuits. Is everybody okay with this? It's not too much. It's all okay for now, né? Yeah. Are you going to give us all the formulas? In the test, yeah. But you will only need this, right? Because this formulas is the only ones you're gonna need. But I will definitely give um what is this now? A formula sheet that has all of this in. Okay. Okay. Looking for a nice example, yeah. Okay, here's a nice one. Let's start with this. Does anyone have any problems with this so far? Can we start with an example? Does anyone not know where I got a value from or something from? You should speak now before we continue. If so, please stop me. If you're lost anyway, don't just sit, quiet and scared to speak. No, no, I need this page. I'm gonna use this page as my formula sheet. this question, let me write down this thing. Okay, so number one, saying we have a resistor. So it's an RLC circuit. Yeah, it's an RLC circuit. So this one, as you can see, now, this is the RLC circuit. Yeah, you can see that now. Yeah, why is it so blurry now? This is the RLC circuit. This is the RL circuit. This is the RC circuit. Just so you know the names of the things. It's the components that is in there that give it the name. So this is my resistor. That's my inductor. That's my capacitor. This is my AC supply. This is, so the saying our voltage is 200 volts. Our frequency, it's 50 hertz. The resistor's value is 25 ohms. The inductor's value is 0.19 Henry. The capacitor's value is 125 microfarads. Okay, question 1.1. 1.1 is saying we must calculate the circuit's impedance. We must calculate Z impedance.
I'm sorry, sir. What page is this one? It's not textbook.
Yeah, it's in our textbook. It is this one over here. It is page 52. Page 52. It's this July 2014. We can.
I don't have that.
Oh, should I take a picture for you and send the group? Or do you know? As a first edition. By Donkey. So impedance. And we know that impedance is the total resistance. Our RT, right? But we put it as the Z for impedance. Just a fancy way of saying total resistance. Okay, so knowing now what we learned, right? We need, for the full resistance of the circuit, we need to get all the resistances of each component first. We have the resistance of R, we have this one, fine. But we need to get these two now. Okay? Because we have all the components, we have R, L, and C, we have to use the formula for impedance that has the R, the L, and the C. So it's only going to be number 8 that we're going to use, right? That is straightforward. So we have R squared plus XL, that symbol XC. I think the symbol is called a tilde symbol. So whichever one is bigger, you put in front. So we have our R value, which is 25 join. Okay, guys, just a heads up that this Teams meeting is going to end soon because this isn't the premium team, so it's gonna cut off at 60 minutes. Then we just all join again. We just all join again. So my next step is to get my XL, right? I'm gonna get my XL, and I know I know, yeah. So my XL formula, it is saying 2 pi FL. So I write down my formula and I substitute. My frequency is 50 hertz. My L is 0.19, 0.19. Then I put it in my calculator. So calculator, right? Is calculator work can be a bit of a problem. Sometimes depends now. If you use it often and you change modes and all that a lot. Whatever what you should be doing is you press shift, you press number 9, you say all, yes. So what I did is I'm clearing all the functions that is maybe it's in a different mode, and when I calculate I get different answers. So shift and 9 for clear, basically clear all the modes. Put it on default basically. I say all, yes, okay, now we can continue. So 2 times pi times 50 times 0.19 equals to, you see I put it for the decimal. The correct way is to keep it, for me, right, for me personally, I would keep this 19 pi like that, but write it again and I will say 59.69, yeah, 69 in ohms. The reason for this is if I round this off and I round off my XC value, when I put it in here, I'm gonna round off again. When I get my current, my total current, I will use rounded off values to get my current, and I will be off maybe by a few. I will be more accurate if I use this in my calculation. That's 19 pi. I will be more accurate. This is just how I would rather work just to get a more accurate answer. It won't be incorrect, but use this one rather for me personally. Because this is the actual answer, like fully. This one is rounded off. The back decimals, I can't, I'm not gonna write all of them. But you can write all of them, but to type it in all again is a problem. Sometimes you have to because there's no fraction. Okay, for XC, my formula is 1 over 2 pi FC. I substitute my 50 hertz, and my capacitance is 125 times 10 to the power minus 6. Does everybody know the scientific notation? Does anyone not know that this microfarad is 10 to the power minus 6? So 25, comma 4647908. That's in ohms. You see, this one here doesn't have a fraction, so it's the full decimal. That's why I wrote it. You don't have to write the whole thing in the calculator again for this calculation. You can if you want to, but let's save time and not do that. So we can do, let's try and do all the examples today. So, okay, so my XL is bigger than my XC. So I'm gonna write it first. I'm gonna say 59,69, 59,69 minus 25,465 squared. What I do now is my calculator, divide squared plus 59,69 minus, 59,69 minus 25,465 squared equals to 42,383 ohms. That's my impedance. Straightforward, finished. Then they ask for the current, total current. So I, but they want I total. I total equals to, this is Ohm's law, my V over Z, V over R basically, right? So my voltage is 200 over there. This 200 is my V total. My V total. So I have my 200 over 42,383. 42,383 gives me 4,719. Straightforward, right? So now they're asking for the voltage drop. Well, they say voltage across the resistor, and for that we're gonna need the current and the component's resistance. So for the voltage drop of the resistor, we need the current multiplied by the component's resistance, so R. This is Ohm's law, right? V equals I times R. That's all what voltage drop is, or to say voltage across, the very same thing. So our I is 4,719, and then our resistance is 25. Can someone just punch in a calculator that answer there, please? And I will carry on with the next one. Oh, 1.4. With the voltage drop across the inductor, we have our VL equals, we need the current through this component, which is I total, because it's a series circuit, the same current. We need our I total times this component's resistance, which is XL. This is still V equals I times R. Our I is 4,719. Our XL, it is 59,69. Can someone do that one also? For VC, voltage drop across the capacitor, or our voltage across the capacitor, we need the current going through, which is our I total, and we need the resistance of this component. So it's our I total multiplied our XC. That's also on our formula sheet that we wrote. VR equals I times R, VL equals I times XL, VC equals I times XC. Okay, so the voltage drop of the capacitor, it needs the current and its capacitance, its capacitive reactance. Our current is 4,719. Our XC value is 25,465. Did anyone get these answers yet, or should I press them myself? Times 25. I think from tomorrow, yeah, from tomorrow, it would be nice if you guys can participate because, yeah, I know that if it's difficult, just try to attempt something, all right? Don't just, sit there not understand. So if you don't understand, please feel free to ask at any time. So this is 117,975 volts, 59,69. For our voltage drop across the inductor, we have 281,677 volts. For the capacitor, our voltage drop is 25. It's 120,169 volts. Okay, so they're asking for the phase angle. For phase angle, actually, you do get more than this formula. You get a formula with tan as well. Where did I see that now? Okay, but we continue, we do this one. Uh, phase angle. So theta equal to cos secant function R over Z for phase angle, eh? Number 13 here on our formula sheet. What we do is we substitute because we already have these values, right? Our R value here is 25. Our Z value is 42,383. Theta equals to 25 over. Therefore, our phase angle equal to that. Let me see something quickly. Where is that value? Um, second function. Uh, okay. Oh, that's for that. That is for that. That is for that one. Yeah. Phase angle, we stick to this one, yeah. Okay. This is the first calculation. It's finished. Question is finished. So let's do another one. Let's do another one. For number 2, we have again a resistor. So we have our AC supply. Our V total is given as 110 volts, and our frequency is at 50 hertz. We have our resistor, our inductor, and our capacitor. Our resistor's value is 20 ohms. Our inductor's value is 20 millihenry. Our XC value, we are given this. Our XC value is 13,3 ohms. This is the question over here. This is just read out everything, read through everything. So they are saying for the first question, calculate the value of the capacitor. Let's read the questions over there. Calculate the value of the capacitor. So we're just gonna manipulate this formula. This is all we do, or not all we do, but what we do a lot is manipulate the formulas. Then they could ask you, so you need to know how to manipulate formulas, you know? So Xe equals to 1 over 2 pi Fc. Before we put values in again, let us first manipulate this before you substitute in a value there and a value for the frequency just to get the capacitance, right? That's gonna make your life much more harder. What we're gonna do now is this. So in mathematics, right, this is 1 over 2 pi Fc. But this Xc is basically, it's a whole number. It's a whole number, but it's over 1. Technically speaking, it's over 1, right? So to get this out of the fraction, we are gonna have to, who knows what we're gonna do now? Can anyone tell me?
Okay.
We're gonna what? Cross multiply, right? Cross multiply. So that just means we're gonna have this. So the 1 times the 1, we're gonna have 1. Okay, 1 times the 1, we're gonna have a 1 one side. Xc times 2 pi Fc is gonna leave us with Xc 2 pi Fc. We are still together, right? Just cross multiplying. Now, to get C alone, what do we do now? To get C alone, we divide.
You bring up the
Yeah, we divide with everything here. The Xc2 pi F. We divide with that. Then we're gonna get 1 over Xc2 pi F. So we get. So if we write this nice, just switch it around so we can, so it looks better. Basically, it's this now, eh? 2 pi F Xc. Basically the same thing. It's the same, very same thing. Not basically, it is. Now we substitute 2 pi. The frequency is 50 hertz. Our X value, which is given over there, as 13,3. Calculator 1 over 2 pi 50 times 13,3. Oh, put it out times. So we are given minus 4. Okay, can't see. We are given to the power minus 4. But we really wanted in that form. We wanted maybe in a form we're used to getting. So this is micro. This is why it's important to know your scientific notations. So the value of our capacitor is 239,331 microfarads. Microfarads. Are we together on this first question? Are we together? Okay, lovely. That's good. For the inductive reactance for question two, the inductive reactance, let's do it like that. Inductive reactance, XL is our inductive reactance. XL equal to 2 pi FL. 2 pi FL. Now all we do, we substitute our 50 hertz. 50 hertz, the value of our inductor is 20 millihenry. So 20 times 10 to the power minus 3. Calculator. Equals to 6,283 ohms. Always your reactance values is in ohms. See there it's in ohms, our XL is in ohms, and our XC is in ohms because this is the resistance value of our component. Okay, every time there, very straightforward. Then they're asking for the total impedance. The total impedance. Total impedance, so Z equals. So I don't know the formula, right? So I look at my formula sheet for the impedance of my circuit because I have my R, L, and a C in my circuit. I don't just have I don't just have a two-component circuit. It's a three-component circuit, this one, eh? So I look to this one, the big one, and I see, okay, for impedance, the formula is saying R squared plus my XL, the total symbol, XC squared. Okay, now all I do is I substitute because I have my XC value, I have my XL value, and I have my R value. So all I can do now is to substitute my 20. So my XC is bigger than my XL, so I'm gonna say by 13,3 minus 6,283. Remember what I said? Whichever one is bigger, you put first. And here my XC is bigger than my XL, so I put it first and I subtract a 6,283 of my XL. Does it make sense? Are we together there? I like to hear some feedback so I know we're together. Lovely stuff. And then our impedance is 21,195, and it's in ohms because it's total resistance. We finished there. Then they're asking for the total current of the circuit, our I total. And for I total, all we do is, it's our Ohm's law. I total equals to V total over our total resistance. This is our Z. So our voltage is 110 volts. Because it's given over there, it's 110 volts. Our Z is 21,195. So it's 110 over 21,195. And our current is in amps. Our current is always in amps. Very straightforward, right? The next question is saying the voltage drop across the resistor. Voltage drop across the resistor. So they're asking for the voltage drop across the resistor and the voltage drop across the inductor. So Ms. Jacobs. Ms. Jacobs. Can you tell me the formula for the voltage drop across the resistor, please?
It's IT multiplied by.
Yes. So VR equals IT times R. So IT is 5,19 and our resistor it is 20. So 5,19 times 20, 103,8 volts. So 2,6. Mr. Daniel, can you tell me the voltage drop across the inductor? The formula we need.
Multi guy, multi.
For the inductor now. For the inductor. Did you say times XC? Did you say IT times XC for the inductor? That is incorrect, sir. Because this here, it's our resistor, right? We know this one. That's our resistor. This is our inductor. This one here is our capacitor. So we want the voltage drop. We got this voltage drop here. So this is VR. That's our VR. And then this is our VL. The voltage drop across the inductor. And then this will be the voltage drop across our capacitor. So we are looking for this voltage drop across here, the inductor. I think you're confusing the names, meneer. You're confusing the names. So we need this voltage drop across here. So what formula will this be? Yes. IT times XL. The IT times XC will give us VC, but they didn't ask this, they asked for VL. So you must just be aware of the names and the symbols for them. So our IT is 5,19, our XL is 6,283. Equal to 32,609 volts. Okay, now they're asking for the phase angle. The phase angle is equal to cos second function R over Z. So I remember from my formula number 13, theta, um, my phase angle equals to second function cos R over Z. Does everyone know to get that second function cos on the calculator?
Yes, sir.
Okay, so here we have our normal ones, right? This is the normal cos. If you press it, this is the normal cos. But we need second function cos. So if you see in the calculator, there is this yellow or different color um, writing above that button. So you press shift and then you press cos again. then you'll see second function cos. If you press shift and sin, you will see second function sin. If you press shift and tan, you will get second function tan. Does that make sense? Cool. So we can have second function cos. Our R value is 20. Our Z value is 21,195. So second function, so I say shift cos, and then I have 20 and a fraction 21,195. It gives me 19,332 degrees. And that is finished with that question. Yeah.
I see in the book these examples of.
I say we stick to cos. We stick to cos. I know that some they do have other phase angle formulas. Like where is that other one? See here in the text, for example, they use cos. They use cos over there. Um, they use cos over here for the phase angle. Um, Here they use cos or tan. But let us see if we're gonna get that same answer, right? So this formula, it is saying tan theta equals to xl minus xc over r. To make this more simple, we say theta equals tan. When you take this tan to the other side, it becomes second function. That's mathematics, right? So let's use our values that we have here. Let me see if we can get the same answer. Hopefully we do. So our XL, our XL is smaller. Our XL is smaller. So let's put our XC first. ABC 13,3 minus 6,283 over R, which is at 20, equals 2. So for my second function 10, I'm gonna say shift and 10. We have a fraction, so 13,3 minus 6,283, 20. Yeah, we get the same. We get the same answer. Could you see it in the calculator? Yeah, we get the same answer. You can use it. Yeah, we have proven you can use it. I'm gonna say it's good to know more than one formula for the thing. Very good to know. But in these calculations, you can always get any variable, not any variable, but you can get any value of any component that you want. You can get it if you do it step by step. You can get anything you want. Anything. Like, let's say the first question they ever asked us, alright, was get voltage drop across the inductor. We will need to get I total. We will need to get XL. To get XL, we're gonna need to use this. We can use F, and you can also use L. To get IT, we must get Z first. We must get Z first. We must get XC and XL. All that run around, but we will still get our answer. So you can use this tan for the phase angle, which is proven now we get the same answer. You can definitely do that. But you can always trust one formula. If you're comfortable and you know that it works, 100% go for it. It's up to you. As long as you get the same answer, I'll be happy. Okay. It is 8 o'clock, but we can continue. If you guys are up for it, I don't mind. Yeah, I want to do this one with the resonant frequency. Okay. Number 3. You can do this one quickly.
On what page is that, sir?
This is on page 53. On the first edition textbook, that red one. I can send a picture of it. Let me send it now if you want the picture.
I have it in front of me.
Okay, cool. So this one I want you guys to do with me. With me would be very nice. So we can end the night with working together this nicely. So for the inductor, we are given 40 ohms. For the capacitor, we are given 60 ohms. They are saying we must calculate the following, which is Z, I total, L, C, phase angle, and then resonant frequency. Okay, so let's do this together. I hope you guys are having a book in front of you, writing, doing something. So, what do we have firstly? What do we actually have? Okay, Mr. Daniel, can you tell me, sir, what is this value here given to us? What is the name of this value actually? Can you tell me?
Inductive.
It is the? No. Inductance is given in Henry. So, let me write it like this. Inductance is given in Henry. Capacitance is given in farads. I don't think I wrote down. I think I just said it. But let me do this. Yeah. So this value is my inductive reactance. This value is my capacitive reactance. This value is my inductance. This value is my capacitance. So, looking at this, what is the name of this value, this 40? Yes. So, otherwise known as my XL. That means that my 60 is called my XC, my XC value. This is how you must evaluate your circuit and the given information. This is the steps you must take. This is not the steps, but this is your first thing is to observe what you have, what you've been given. Okay. So question one is get the impedance. So let's do that. Which formula am I gonna use? Which number? Can someone tell me?
3.
For our impedance.
I mean number 8, but number
Yeah, number 8, but number 3. It's the same thing, that one. Okay. um, XL XC squared. Okay. So I must see now the bigger one I put first. So XC is my bigger one. So I put it first. My XC is bigger, so I'm gonna say 60 minus 40 squared. Let me just put over here. I'm gonna say bigger one, bigger one first. Yeah, just so we know. Okay. Calculator, which is where now? Oh, yes. Okay. Square root 25 squared plus 60 minus 40 squared. Always remember the square root, very important. Your brackets here when you square, very important. And the square there for the 25. So our impedance value is 32,016, and it's in ohms, right? It's in ohms. Number 2 for I total. So our I total you guys must tell me the formula for this now. This question we're supposed to do together. This last one.
okay, it's
B.
total over Z.
Yes. So we have 220 over 32,016. Hardly stuff, okay. So our L. So they're asking for L. And the only way we can get L is to manipulate the formula. And the only formula we have right now, okay, if you can see here, this formula here is for our resonant frequency, number 14. It has our L and our C, but we don't have our C and our L, so we can't use this. We can't manipulate, and we don't have our resonant frequency even, so we can't do anything. But we have a formula that includes the L and we have the value of our XL. So all we do now is we manipulate this one. So XL equals to 2 pi FL. And we do the same thing, we get L alone, and to do that, we divide with this 2 pi F. We divide with that 2 pi F, and we're going to be left with, it's going to look like this, 2 pi F. I know my 2 can look like a Z, but it's not the 2, that one. I write it nicely. So now we substitute my XL value for my inductor is 40. I write my 2 pi, I write over. I write my 50 hertz. Now I calculate this thing, 40 over 2 times pi times 50 equal to 0.127 Henry. Let us say, just for interest sake, right? Let's say they ask for the value of our inductor, but they say put it in millihenry. So all you're gonna have to do, right? All you're gonna have to do on the calculator, let me put it here, we can see. There's this engineering button that you can press to move the comma, the decimal. You can move it, then you say to the front, then you say, when you see 10 to the power negative 3, that is our milli. So it's gonna be L equals 127,324 millihenry. If they want it in micro, we press it again, but it's too big now. But it's going to be 127,323, okay, let's just write it, man. Just for the knowing. Micro Henry. This is all the same value. We just wrote it different. This one is more accurate because it has more numbers in, but it's very same value. But just for interest sake. So number four. Number four, it's saying we need the capacitor's value. And we did this question before, right? We did this one before in the previous one. So we just do this quickly. Cross multiply now, yeah? So, okay, let's put it here. Okay, the one is the xc 2 pi fc. Then we need c alone. So we're gonna divide. We are gonna divide with this, with these over there. Then we're gonna get 1 over xc 2 pi f equals all c. Then we write it nicely, and we're gonna get 2 pi f x c. Then we're just going to write it. Our frequency is 50. Our xc, is a 60. C equals 50 times 60. So this one is to the power -5. So only we press that engineering button, or the English button. Now it's to the -6, which is Micro. Micro farads. That's our answer. We put it in this form, right? To -6 because capacitance it's normally given in micro or milli. Um, that's why for the inductor, inductance is normally given either in Henry, just like this, 0.127 Henry, or it's given in millihenry. It could be given in microhenry. This is just for intrinsic and to know because they could give it in any way. They could ask you to put it in any form. Then you must know. Now for the phase angle, we have the formula. Which formula we're gonna use? Which formula do you guys wanna use? Do you wanna use the cos or the tan? You can decide. Okay, so cos second function cos r over z. This is coming from my formula sheet number 13 here by us. So what I do is I substitute now, and my R value is 25, my Z is 32,016. Second function. For second function, I say, okay, Mr. Daniel, can you tell me how do I get my second function cost? Because you didn't know early this evening. How do I get my second function cost? Can you tell me? Are you still with us? What did you put? Yeah. Yes. Shift and cost. 25 over 32,016 will give us 38,661. 38,661 degrees. That is our phase angle. Now our resonant frequency. Our resonant frequency. So if we can say if okay, if that f0, okay, so 1 over 2 pi square root LC. So I'm making this like this for a reason because as you can see, so if I use this one here, if I use this one here at the bottom, right, my answer will be more accurate because I have more numbers of this decimal, right? This will be more accurate. So what are we gonna use? Let us use okay. Let's use this one, the last one. Let us be accurate because we want to be nice and accurate. 323,955. Put this in brackets. Multiply. Okay, yeah, just put it like this. Micro multiplied by 53,052 micro. Yeah. So this micro is 10 to the power -6. I don't have much space, that's why I did it like that now. So all we're gonna do is this. 1 over 2 pi times the square root, like that. I hope you can see the screen there of that thing. So my decimal is 127.323,955 times 10 to the power minus 3 times my capacitance now, which is 53,052 times 10 to the power negative 6. I press equal. So 1,936 is my resonant frequency. 1,936. Yeah.
I don't know.
Didn't I do that on the calculator? Oh, yo,
Yes.
yeah, I did. Look, when you tell me, yo, yeah, you're right. Thank you. To the 6. Yeah, this is why your sign is very important. Very, very important. You'll be much more accurate. So 61,237. Let me actually see something. I want to see something. Hmm. Dun, dun, I see, I see, I see. Okay, yeah, this is our answer. 61,237. Our original frequency. But I will be okay. Let us do this. Can you all this last question, alright? This question here, we didn't do it now. But this question tomorrow, first thing, we mark this thing. So everyone must try it. We're gonna do this one. I will try my best to find. I will definitely find calculations on past papers on this paper because there is a calculation I want to do when the circuit is at resonance. It's a bit different. But actually, it's easier. It's much easier. But I want to do it with you guys, so we are exposed to all of the different circuits we get for RLC. But yeah, we can call it a night, and then I will send a picture of this one now quickly in the group so that we can do it for the homeworks. We can say homework, not homework, but yeah, so we can mark it tomorrow. Is everybody happy so far? What did you get? So you got 61,333. Now you see what I meant by you will get different answer because the micro has more decimals in than these ones. So for sure you will get different answer. For me, the more numbers you have in your decimal, the more accurate you'll be. Way more accurate you'll be. Without a doubt. Okay. Yeah. Um for me, right? calculations. Those calculations is maybe new, or it's still, but but new to many people, to a few people. So I would go to that more.